Mrs. Vara here. This video is going to be the first part of the Chapter 3 notes, so Section 3.1 for calculus. So we're continuing with derivatives or differentiation in Chapter 3, and Section 3.1 is all about what we call the chain rule. So it says, let's introduce a new differentiation technique by showing you types of functions that would require its use. The table below illustrates pairs of similar functions that can be differentiated with or without the chain rule. Up here it says, calculate derivative of compositions of functions. So just a little refresher of what a composition of a function is. So it could be identified that way. We looked at these in pre-calculus. Or that way. This one I called fog. It has the little open circle. And when you compose two functions inside of each other, and whether you compose f of g of x or g of f of x, if you get x for an output, that means those functions are inverses. This could also be written, g of f of x. So this is f of g of x. G of f of x, if you compose two functions both ways and you get x for your output, that means the functions are inverses. So compositions, you can think of them like a function inside of a function. So sine of x is a function. X squared is a function. If I put sine of x inside of x squared, I'm going to get sine of x squared. So sine is on the inside, the squared is on the outside. So sometimes you can see that they're a function. Square root is a function, and x squared plus 3 is a function. So this is a composition. So you know how to take the square root of the outside. The square root of x is the derivative of the square root of x is 1 over 2 square roots of x. You know how to take the derivative of the inside. The inside of that would just be 2x. What we need to learn is how do you take the derivative when you have one function inside another. Okay, so this is showing you some examples of functions. So this is y equals x squared plus 1. This is not a composition. This is a function and this is a function. This is two functions added together. So can be differentiated without the chain rule. This is a composition. I've taken this function, x squared plus 1, and put it inside a square root. So this is a composition. So this you would have to differentiate using the chain rule. Sine of x is just a single function. You could take that derivative right now if I asked you. This is a composition. I'm going to put some parentheses around here. So sine of x is a function. You can think of that as sort of the function on the outside. When I read left to right, I come to sine first. So sine of x is the function on the outside. 6x is a function. That's a linear function. That's the function on the inside. So this is a composition. You have to use chain rule on that. 3x plus 2 is a line. That does not require chain rule. The derivative of this is 3. This is a composition, and it looks like a composition. This is the inside function. The outside function is x to the 5th. So I've replaced x with all of this. So this is a composition. X plus tan of x, you could take the derivative of this. Right now, the derivative would be 1 plus secant squared. This I could take the derivative of right now. That would just be 1. It's the second part that is a composition. Okay, so this I would just take the derivative of plus the derivative of this, tan of x squared, would require chain rule. Okay, this is the definition of chain rule. So this says if y equals a function, so y is a function that has the variable of u, and it says it's differentiable. And then they say it's a function, a differentiable function of u. So that means the variable in f is u. But then it says u is another function. So picture if u is equal to g of x, then y is actually f of g of x, right? Here they're saying u is g of x. This function is f of u. So I could replace this u with a g of x, and I would have this. So this is a composition. So right here, they're just defining a composition. They're saying the function on the inside is also differentiable, but the variable on that function is x. So then it says y equals f of g of x. There it is right there. I guess I didn't have to write it. Is also differentiable. So in order for a composition to be differentiable, both the outside and the inside function need to be differentiable, because this starts out if f is differentiable, that's the function on the outside, and g is differentiable, that's the function on the inside. Then the composition is differentiable, and this is how you find it. So let's talk about this notation. So this dy dx means I'm taking the derivative of y, that's kind of messy, with respect to x. With respect to x. So that means I have a function that I'm calling y equals, and the variable in that function is x. So for example, this is a function y, and the variable in it is x. So if I'm taking the derivative of this function, I'm taking the derivative of y with respect to x, and I would get 2x. So they're saying if you're taking the derivative of y with respect to x, which is this function right here, then I'm going to do dy du. So this says I'm going to take the derivative of y with respect to u, and remember u is what g of x is equal to, and then I'm going to multiply it by the derivative of u, this is u, with respect to x. Now if you notice this side, these du's, I'm going to do this in pencil, these du's would 1 out. So this is equal to dy dx. So this right here is actually an important thing that you will use to solve problems. So dy dx is equal to dy du times du dx. These two matching are what you want to pay attention to. So this says, or here's another way to look at it. Here's my composition. So now they're kind of leaving out the y, and they're just saying, this is my composition. This means I'm taking the derivative with respect to x of this composition. Okay, now this says is equal to f prime. So right under here, this is the derivative of the outside. So this is the derivative of f. You can kind of see that we have plain old g of x inside there, times g prime of x. So the way you want to think of this is the derivative of the outside with the inside unchanged times the derivative of the inside. So this is derivative of the inside. I think I'm going to show you kind of really quick up here, and then we're going to do a lot more of these, but I'm just going to show you really quick. if I look at this composition, this example that they gave me, the function on the outside is the square root of x. The function on the inside is x squared plus 1. So this is like my f of x, this is like my g of x. F is on the outside, g of x is on the inside. So this says, take the derivative of f of x, but leave g of x inside there. So now let's say I'm doing the derivative. So d dx. It says take the derivative of the outside. So the outside is square root of x. The derivative of the square root of x is 1 over 2 times the square root of x. But I'm not going to put just x in there because this says take the derivative of the outside, but keep g of x inside there. So I'm going to keep the inside in there. And then times derivative of the inside. So the inside is the derivative of this, times 2x. Now, we're going to show kind of an easier way to walk through that, but I just wanted to show you what it looks like. This part right here is derivative of the outside with the inside unchanged times derivative of the inside. All right, let's keep going here. I don't know how much we're going to do in this video, but enough to get you started. Okay, so this is kind of a fun little analogy for you to use for a composition. So think of a composition as a function inside a function. The hard sucker part is the function on the outside. The bubble gum is the function on the inside. So the outer function, y equals f of u, is the candy shell. The inner function, u equals g of x, is the bubblegum center. So we're going to complete this chart now. So they give us a function. It's a composition, and we got to figure out what is the inside and what is the outside. Now, right now, this might not look like a composition, but this says rewrite using parentheses. So if I have a fraction, I know I can always rewrite by using a negative exponent. So these are equivalent. I've just rewritten it using parentheses. Now it says find the inside. This is the inside. So what's the function on the inside? This one kind of looks like it's on the inside. Call it u. Okay, the function on the outside, the candy shell, is the to the negative 1. So we're going to say the outside, our y, is u to the negative 1. So this is the process we're going to go through. We're going to find the inside. We're going to set it equal to u. And then we're going to find the outside. And we're going to say, oh, that's the inside to the negative 1, right? So the outside is something to the negative 1. The inside is x plus 1. You're going to call your inside u and your outside u something. Let's look at another one. Y equals sine of 2x, right, using parentheses. This is kind of like the one we did up there. So this is sine is on the outside. The inside is 2x. 2x is a function. It's a linear function with a y-intercept of 0. Okay, what's on the inside? 2x. So u equals 2x. Sine is on the outside, so y equals sine of u, because I've said u is 2x. So we want to write two functions that aren't compositions, inside and outside. You could take the derivative of both of these. You could take the derivative of both of these. When they were a composition, you couldn't take the derivative. All right, let's try this one. Write it with parentheses to begin. So that's going to be a power of 1/2. So 3x squared minus x plus 1 to the 1/2, because square root is 1/2. Square root is the outside function. This is the inside. So u equals 3x squared minus x plus 1. The outside is the square root, or the 1/2. So it would be u to the 1/2. Okay, tan squared of x is the same as parenthesis tan x squared. Okay, what's on the inside? Tan of x. So u is tan of x. Outside, y is going to be u squared. All right, now let's try at least one of these. Turn the page. Okay, example 2. Actually, we're on our second example. Okay, so find dy dx. Find the derivative of y with respect to x. Okay, so this is a composition. I'm just going to remind you what we're going to do here is we're going to find dy dx by finding the derivative of y with respect to u and multiplying it by the derivative of u with respect to x. Okay, so let's find the inside first. This one looks like, this is on the inside. It looks like it's on the inside. So call that u. So u equals x squared plus 1. Okay, we want to find the derivative of u with respect to x. So this is u with respect to x. So du dx is going to equal 2x. Okay, the outside will be our dy du. So what is on the outside? Y equals u to the third. So the outside is something to the third. The x squared plus 1 is the inside. If I'm taking the derivative of this, I'm finding the derivative of y with respect to u, which would be 3u squared. Now this says if you are wanting to find dy dx, which is what we're wanting to find, you're going to multiply dy du by du dx. So now I'm going to say, okay, dy dx is going to be equal to dy du, which is right here, 3u squared, times du dx, times 2x. Okay, now I'm not done because this says find the derivative of y with respect to x. I shouldn't have any u's over here. This needs to be all x's. So I did take the derivative, but now I want to write everything here in terms of x. So u, right here, we figured out that u was equal to x squared plus 1. So I want to replace this u and call it an x. So instead of 3u squared, I'm going to have 3u is equal to x squared plus 1, x squared plus 1 squared times 2x. And that would be 6x parenthesis x squared plus 1 squared dy dx. Okay, I know I wanted to do this one another way, so I'm going to show you. So this method here goes along with this definition here. Now I want to do another one using this one. Honestly, this is the one that you're probably going to like more and use more. So I know this video's getting a little long, but let me do one more example where I use that other definition. This is kind of a shortcut chain rule. I'm not going to talk about that a lot right now. I'm going to kind of talk about it when we do this example right here. So again, I'm finding dy dx for each of the following. So you want to find the inside first. So here's what you want to think. Derivative of the inside times derivative of the outside with the inside unchanged. You're always going to start by finding the inside first and call it u. So 3x minus 2x squared. So that is the inside. Now, honestly, what I do when I'm doing these, I say, okay, now I'm going to take the derivative of that. I just do an arrow like this. This would not be okay for a free response, but this is sort of how I do it. So the derivative of this would just be 3 minus 4x. Okay, now the outside is y equals u to the third. Okay, I'm going to take the derivative of this, 3u squared. Okay, now let me go back to this definition right here. So derivative of the outside with the inside unchanged times derivative of the inside. So now I want to take those two derivatives that I just took and multiply them together. So I want to multiply them together. So what I'm finding here is y prime is going to be equal to 3 minus 4x times 3u squared. But I need everything to be x-ish. I can't have any u's, right? This says find dy dx. I'm calling it y prime, but these are the same, just a different way to denote it. But I need a function that has all x's. I started out with a function that has all x's. My answer cannot have u's. So the last step is, this is the derivative, but I need to turn this u back into an x. So u was equal to 3x minus 2x squared. So I'm going to turn that back into an x. So I'm going to use a bracket here because I'm going to have 3. Replace the u with 3x minus 2x squared. And this is u squared, so that would be squared. Kind of a messy looking one. Now I want to show you. The derivative of the outside, if you go back here to the original problem, the derivative of the outside is something to the third. So if I'm taking the derivative of something to the third, I bring the 3 down in front and minus 1 from the exponent. That's this right here. So this is derivative of the outside with the inside unchanged. So this is this part of that definition on the other page. It's derivative of the outside. The x, the something to the thirdish is on the outside. So 3 something to the second power, that's the derivative of the outside, times the derivative of the inside was the 3 minus 4x. This is the derivative of the inside. So this matches up. I can maybe put these both on the screen at the same time. This matches up with this. Derivative of the outside with the inside unchanged, derivative of the outside with the inside unchanged, times the derivative of the inside. So this is my y prime or my dy dx. Okay, I think I'm going to stop that for now. That's a good start, and we can keep going with these in class.